alleato. Sì, infatti. Si può anche finestra oggi. Sì. Sarà soltanto un solo file. Grazie mille. So, we considered today we consider the neural net universality theorem, or why neural nets can compute any class function, but not rigorous proof of this fact, but some heuristic explanation of this fact. So for us is important the detail how can possible to construct some neural net which can do the task to calculate any function. So as we have considered, the neural net can easily realize the Boolean function, Boolean operation, Sheffer prime, that is so-called operation not end. And this operation not end can generate all other possible Boolean functions. So in this situation, the neural net can construct incredible Boolean operation of any complexity, which we cannot even imagine what is it. And also, if we consider any function, for example, now we consider only function, yes, one-dimensional function, which depends on one-dimensional argument f of e. Once we convinced that the neural net can calculate this function, and there exists such neural net, and how to construct such object, yes, then we can extend this fact on the case of the function on which depends on several variables, and even on the function which also is some vector function. So vector function on vectorial arguments. Let's consider some complicated, some weakly, yes, very weakly function, f of x, for example, of this shape. And regardless the complexity of this function, there we can guarantee that there exists a neural network that for any input x, the value f of x, or some approximation close to it, will be output of this network. That is, you see, there exists some neural net, for example, such configuration, which having as input some value x, return us as output the value of the function f the point x. So the result holds even if the function has many inputs and many outputs. For example, in x1, x2, x3 on 3 variables, and the function has two components also, f1 and f2. So really vectorial function defined on vector arguments. This result tells us that neural net networks have a kind of universality. No matter what function we want to compute, we know that there exists some neural network which can execute this task. So this result is, let's say, the mathematical proof of the universality theorem is based on use of the Unbalanced theorem. There is a representation theorem and some Fourier analysis. And then there is some, I can indicate you some reference if you are interested in rigorous mathematical proof. But we shall consider some heuristic proof of this fact by the construction of neural net which can calculate this function. The theoretical theorem of existence doesn't indicate such construction of neural net. So we interesting from the practical point of view. So we shall consider a simple and mostly visual explanation of the universality theorem. And the questions are, related questions are, why it's true that neural network can compute any function? Then, what are the limitations of the results? Of course, there are some limitations of the results. And the third, how the result relates to deep neural networks. So, I can immediately anticipate that why it is true that neural network can compute, because we shall construct the solution in analogous way as Newton and Leibniz constructed the definite integral mathematical formulas. What are the limitations of the result? We shall discuss about this because, of course, it is something like approximation of the function, something like, for example, spline approximation, polynomial approximation. So we can approximate the function with some grade of fidelity, which we can choose before our statement. So we firstly can choose some small parameter, positive parameter epsilon, and we can do some function which can have mean square deviation from our function smaller than our epsilon which we choose before. And the other limitation is the continuity. You see, all our procedure to use our training procedure are continuous. So if a function permits some jumps, it is not good for neural nets. But in a lot of situations, approximation of a jump function or discontinuous function by continuous function have some reason, and in these cases, special cases, which it is major part of cases. So we can bypass this problem by use continuous function as approximation of some discontinuous function. And how the result relates to deep natural work. First of all, we shall construct this neutral work network. What is the grade of it? It is deep grade. It has only one hidden layer. So we have one node of input. It is X. Yes. One neuron of input, one neuron of output, f of X, and some hidden layer which contain several pairs of several pairs. There is some parity of neurons in hidden layer. The ability to compute an arbitrary function is truly remarkable, but is also truly remarkable any passage to limit in the mathematical sciences. This jump of quality. Almost any process you can imagine can be thought as a function of computation. For example, problem of naming a piece of music based on a short sample of the piece. So it can be thought like image like a computing function. And almost all possible operation in modern different range of knowledges. For example, problem of translation Chinese text into Italian. It is also can be thought as computing function. In fact, many functions, since there are many acceptable translations of the same text. Several functions. Consider the problem of geometric phase characterization. It is not very large function. Now, again, it is a kind of function, computation of some function. Universality means that in principle, neural network can do this thing and many more. There is some subtle ties, subtle ties, which contain in informal statement a neural network can compute any function. First subtlety is. This doesn't mean that a network can be used to exactly compute any function. It is some approximation, of course. Rather, we get an approximation that I told about. Yes, it is some repeating. So we can define some grade of fidelity, and we can construct some neural net which approximate our function with the fidelity not less than our epsilon, which we have defined before. So, by increasing the number of hidden neurons, say, firstly, we considered some generic configuration of neural net with 3 neurons in the hidden layer, and then let me increase in 5 to 5, from 3 to 5. So in this situation, we can improve the precision of approximation. So, strictly speaking, having a function f is a desired accuracy epsilon some small number, positive number, means the following, that we having f, we can construct some neural net with whose output g of x, yes, output g of x satisfy module g of x minus f of x module smaller than epsilon for all inputs x. So it is uniform estimation of precision, yes, for the interval of definition of the f. In other words, the approximation will be good to within the desired accuracy for every possible input. And second, sub-3D, the class of functions which can be approximated in the desired way are the continuous function. So I talked about this problem. So let us construct a neural network which approximates a function which just one input and one output. So consider some enough complicated, enough complex function, not trivial. Okay. For example, this shape of function. Let's start with a network containing just a single hidden layer with two hidden neurons and an output layer containing a single output. So we have one input, yes, x, one output, and only two hidden layers. We have this method to construct any precision network to calculate some function, and we can improve its precision by increasing the number of neurons which present in the hidden layer. To get idea how components in the network work, let's focus on the top hidden neuron. So let us focus only on this top hidden neuron. As we learned yes before, what's being computed by the hidden neuron is sigma. Our sigmoidal function is of activation. Sigma of wx plus b, where sigma of z 1 divided by 1 plus exponential minus z is the sigmoid function. So what is this comportment? So we have now this function and we have two parameters, yes, weight and bias. For example, 8 and minus 4. So the diagram below shows how the function computed by the top hidden neuron, this neuron, how they change. So first diagram show us that having, for example, w fixed equal to 7, but now we change only the bias. And we can see the move of the graph of this function, of activation function. Then we fixed bias, and we move the weight function. So we have other transformation of the graph. And what are the transformation of this graph? so we can see that as the bias, as the bias increases, the graph moves to the left. With a decreasing, if it decreases, the graph moves the right, but don't change the shape. The shape is the same, yes, the form is the same, only it can move to left or right. So, in addition, it can be seen that decreasing weight, the curve straightens out. So, when now we pass to the weight, not bias, it's clear. Doesn't change the form, yes, the shape, but only move this graph to right or to left. But for the weight, when decreasing the weight, the curve straightens out. So it is tend to be a straight line, yes, linear recta. But with increasing weight, when we increase weight, the curve will become steeper, steeper, and eventually approach to the step function. So by increasing the weight, we can get almost a step function, yes, jump. So 0, then 1. Below there is a plotted of such situation. So W is equal about 1,000, about 1,000, and B equal to minus 400. In this situation, we have a jump function, which is very beautiful, because if we have some curve function, it is very, very complicated to manipulate several functions, for example, to add some function and to add some weighting sum of this function. But if we have such jump function, it is a very simple object. So we can combine several such, but because what we should do with these neurons in the next, we should calculate the response at any node, in the sense that then we should calculate the response of this the output neuron, and it is a result of this network. Okay, so we have sigmoidal function, but this sigmoidal function now we abstract from. So we now pass on this special situation, the jump function. So we begin to approach to construct some small rectangles which approximate some functions. So the same as
University of Rotterdam так може зачинитися, перш ніж ви дістанетеся туди.
чорна тача. So it is very, very useful object that for which we can approximate several actions in this network by calculating the weighting sum of some object like jump functions. So it makes things much easier to assume that our hidden neurons are outputting step functions. In this situation, it's very easy to calculate. At what value of x does the step occur? Absolutely clear that in this situation, when we have B and W, so the position x of jump is precisely S minus B divided by W. So we can introduce a new parameter as, yes, it is the point of jump of our elementary step function. And in this case, we can substitute S and to forget about B and W. Remembering that there is such reconstructive relation between them. So, for example, of course, this jump is not precisely vertical. For example, for W equal to 100 and B equal to minus 40, jump function is some smooth function like logistic function, but it approximates a jump, a step function. And the position is 0, 40. So it is minus B divided by W. It will greatly simplify the description using just a single parameter S. So we now temporarily exclude our natural parameter of neural net, biases and weights. Forget about this and operate only by S. So in this situation, we can rewrite this neural net and the corresponding output from the top hidden neuron. Okay, top hidden neuron. In this situation, so X go to this neuron which has the response S equal to 0, 40. So it is 0 in the point S 0, 40. It jumps to 1 and then remain the constant. And we have only one parameter. So we have implicitly set the weight W on the input to be some large value, big enough that the step function is a very good approximation. Really, it should be about 1000, really. We can easily, unfortunately, the weight should be very big to have jump elements. We can easily convert a neuron parameter. So having this S after, we can then easily to recover the bias B by the formula minus WS. So now we look at the behavior of the entire network. So firstly we considered only the behavior of the upper hidden neuron. Now we can adjoin all our network, because now it is clear that the same succeed with the second neuron. So we suppose to consider hidden neurons are computing the step function parameterized by step points S1 top neuron and S2 bottom neuron. So, and they, of course, they adding, yes, and they accumulate our jumps. So this is typical behavior, yes. This is typical behavior of a complete such network. So we have entry value X, then it goes to S1 040, for example, and S2 060, okay? Then then there is W1, it is some weight 0.6, for example, and W2 1.2, for example. So we have such comportment of W1 plus W2. So this chart means that the weighted output W1 A1 plus W2 A2 from the hidden layer. A, of course, activation function for first and for the second hidden layer. So now by stating W, we are free to choose our parameterization and to see the response on several nodes, on several levels. So now we choose W1 0.8 and W2 minus 0.8. What happened? We have some bump function. So we have constructed our elementary rectangle.
Lo schermo è utilizzo?
Sì. Condividiamo il file. Sì. Perfetto. Allora, manipolando così con due by manipulation of two weights, you see W1 and W2, which are symmetric, yes, 0.8 and minus 0.8. We have constructed the rectangle, yes, the bump function. So now we need to introduce a new parameter, h. It is what is it? It is text. Highness of our rectangle. Highness of our rectangle. So we now introduce a new parameter. Yes, and now we should remove S1, S2, and so on. So we S1, S2 will write inside the node, and H we shall write down as instead of the weights 0.6 and minus 0.6. So now one can use our bump making trick to get two bumps by gluing two pairs of hidden neurons together into the same network. So we can glue other two neurons, okay, in the sense that we have some continuation of our rectangles. So we construct, we gradually construct the discrete approximation of our function. Yes. So we have now the 0, then S11, S12, S21, S11, S21, S12, S22, and 1. So we have some piecewise constant function which aimed to approximate our function. More generally, we can use this idea to get as many peaks as we want, or any height. So we can now, by manipulating of our S, our H, yes. So the point of jumps, the jumps point, and the highness. We can construct any piecewise constant approximation of our function, roughly speaking. So, in particular, we can divide the interval 0, 1 into a large number n of subintervals and use n pairs of hidden neurons. You see why pairs? Because we create some rectangles, so we should have 2 point of jumps. Yes, 1 and 2. This is why we should have the hidden neurons by pairs. So n pairs of hidden neurons to set up peaks of any desired height. So we can now construct such discrete approximation of our function. So now we return to the function plotted at the beginning of the lecture. So this strange function f of x. It was not told that it is properly the function, polynomial function, polynomial trigonometric function with quadratic terms and 2 trigonometric terms. You see, this is the function 0, 2, and so on, plus 0, 4 x squared plus coefficient 0.3 x sinus 15x plus 0.05 cosinus 15 x plotted over x from 0 to 1, and with the y-axis taking values also from 0 to 1. It can be. So obviously it is not a trivial function, it's a rather complicated function. We are going to figure out how to compute it using a neural network. So we should to construct a neural network with one neuron input output. And the method is the output from the network, the output of in any node, even intermediate, is sigma, yes, activation function of summation, yes, wj, aj, it is the result in the previous nodes, yes, plus b, plus bias in this node. So the solution is to design a neural network whose hidden layer has a weighted output given by sigma minus 1 acted to f of x. Yes? Where sigma minus 1 is the inverse, nothing else, inverse of the sigma function. So the weighted output from the hidden layer should be sigma minus 1 applied to the function f of x. You see, it, of course, transformed. Now it has such form. And the solution is the following, you see. 0, 0, 0, 2, 0, 2, 0, 4. So we have input, then we have 1, 2, 3, 4, 5. 5 couple of hidden neurons. And then we have some H. So it is S. S1, S2, S3, S4. Yes, it is the coordinates of jumps. So, and we have the precision weighted output sigma 0.38. So it is our epsilon. It is our epsilon. And now we can reconstruct from this S and H our neural network parameters. The first layer of weights we can choose arbitrarily, but about 1,000, and we can choose 1,000, for example, for all these connections. 1,000. The biases on the hidden neurons are just b equal to minus ws. So, for example, 0, 0, 2, yes, bias. So bias from 0 to minus 200. From 0, 0, it is 0, yes, because we multiply 0, and so on. So we can really calculate it, the biases of these nodes. And in this situation, the final layer of weights are determined by H values. So for instance, the value you have chose above for the first H, for example, minus 0.66, means that the output weights from the top two hidden neurons should compensate, yes, to create rectangle. Minus 0.66 and 0.6 respectively, and so on. And the bias on the output neuron is by definition 0. So we have constructed this way to construct the function. I will not precise you how it can be extended on the vectorial function on the vector argument, but it is enough enough trivial thing. Only some plot, three-dimensional plot, are rather beautiful with some elementary elements like tau function and so on. But it is some detail. Mathematically, it is, I think, very interesting mode to indicate some. I would say practical proof of this fundamental theorem. You see, it is like something like the Cantor method to prove that all rational numbers is precisely the same power. Yes, some precisely quantity like all integer numbers. So you can calculate. You know, yes, no. So I think we finish today. So if there is no question, I will finish. So it's the one.